Hello and welcome to the course on Research Software Engineering with Python at the University College London. In this episode I'll be talking about data and data formats. My guest is Nick Radcliffe, CEO from Stochastic Solutions and a visiting professor of mathematics at the University of Edinburgh. Nick worked in data science for a very long time, and he's also the author of a Python library called Test-Driven Data Analysis, or TDDA for short, and you'll be hearing from Nick a bit later. But before that, let's talk about some of the popular data formats and where they come from. Data formats have of course existed for a very long time. After all, computers need to be able to understand the kinds of data you give them, meaning you need to set out the structure of the data you pass in. A very simple structure is a list or a table, where each row has a set of columns into which you can insert some values. One of those list-based formats is the so-called comma-separated value format, or CSV for short. And this goes back to the early 1970s and was used by IBM in a compiler for the Fortran programming language. The name itself, CSV, seemed to have appeared in the early 1980s. And CSV files have stayed with us ever since. Their structure is pretty simple. As I already mentioned, they're basically a list of rows where each row has a set of values separated by a comma, but commas are not the only way to separate values, of course. You could also use space, tab, semicolon, or other characters. The values themselves can be anything as long as they can be expressed as a string. And that, of course, is one of the downsides of CSV. In each row, your CSV may contain a wild mix of different data, simple integers, real numbers, strings, or complex types, such as embedded lists or maps. To help programs deal with it, you could add a header row to indicate the type of values, but it remains a very weak binding, and your CSV file, even when it's machine-generated, can contain the wrong kind of data in the wrong place. But CSV, popular as it still is not the only data format. Since then, other data formats have come up that allow much better and more complex structures and type definitions. JSON, for example. JSON stands for JavaScript Object Notation, and as the name suggests, it started with the JavaScript language, one of the core technologies used in web applications and platforms. Two people, Douglas Crockford and Chip Morningstar, are credited with publishing it in the early 2000s. It was first standardized in 2013, and roughly at the same time, another data format was published called YAML, which stands for Yet Another Markup Language. YAML also allows for deeper structures and using data types, but the format is somewhat a little easier to write out than JSON. CSV, YAML and JSON are all text-based data formats and therefore easily portable between different machines, different applications, and different operating systems. But in return, each of them tends to be used for slightly different purposes. So CSV is usually associated with spreadsheet applications like, for instance, Excel. Sometimes you can write out database tables as CSV files as well, but quite frankly, when you have relational databases or more complex data structures, CSV is not a good choice. Which is where JSON comes in. It may have started as a data format for web-based applications, but it's nowadays used in a much wider range of applications. Often JSON is used as a format for exchanging messages and data between applications. It's also used by databases to import and export data tables, and in many ways JSON has replaced formats such as XML. YAML also allows for structured data and data types, as I mentioned earlier. I'm honestly not sure how wide it's used to store data or exchange data. However, it's used a lot as a format for configuration files, for instance a system configuration or application configuration. For all of the formats I mentioned so far, CSV, JSON and YAML, Python has a rich set of tools for parsing and writing data in CSV, JSON and YAML. In addition to that, libraries such as NumPy and others have their own tools to read and write data in these formats. CSV, YAML, and JSON is just scratching the surface. There are, of course, a lot more file formats out there, including proprietary formats for commercial applications. The one thing we haven't talked about yet, though, is when you want to store and process really big data sets, like in data science, machine learning, and artificial intelligence applications. And we're not talking large Excel files here, with a limitation to just over 1 million rows. These are datasets measured in gigabytes or terabytes, datasets that are stored on cloud services or maybe processed by supercomputers. Storing them as CSV, JSON, and YAML files is simply not practical. And there are two formats that I'd like to mention in this context very briefly, called HDF5 and Parquet. Let's start with Parquet. It's an open source project and part of the Apache Software Foundation. Parquet files are stored in a format that allows for quick access, and one aspect of this is that, unlike CSV files, Parquet files are stored based on columns rather than rows. Parquet is used, for instance, in cloud-based services and solutions. HDF5, on the other hand, or to give it its full name, Hierarchical Data Format version 5, is also capable of dealing with large datasets. It started its life in 1987 with a portable scientific data format, the so-called all-encompassing hierarchical object-oriented format, from the National Center for Supercomputing Applications, the NCSA, in the United States. And right there is the clue for its use: supercomputers, high-performance computing, and parallel computing. The format is in fact just a part of the whole package that consists of a data model, libraries, technology toolsets, and many other things. It's maintained by a non-profit organization of the same name, HDF, and has an open source license. There's a lot more that could be said about both Parquet and HDF and other formats, but that would be beyond the scope of this episode. I provide some links in the episode notes if you'd like to follow up on it. And now it's time for my little chat with Nick Radcliffe. Hello, Nick. Nice to meet you again. Maybe you can quickly introduce yourself.
Sure. So I run a company called Stochastic Solutions, which is, I guess we'd call it a data science company these days. So we write data analysis software and do data analysis for people. I'm also a professor of maths at Edinburgh and an organizer of PyData Edinburgh and various other things like that. I've been doing this for a long time now.
Indeed. And you're just the man to talk about data and how to deal with data. So you've been working with machine learning for a long while. So what are the kind of typical data formats? Let's start with that. What are the typical data formats that you've come across?
There are many, of course, and varied, but the sad truth is that the lowest common denominator remains CSV files, what we used to call comma-separated data files, and Microsoft recoined as character-separated data files. You kind of have to be able to deal with that because that's the only thing that absolutely everyone understands. These days, JSON is a lot more common, particularly for web-related things. Obviously, databases are an important source of data, and you can get things in a much more structured format that way, which helps with metadata and formats. There are also the modern sort of JSON-based or document-based databases, things like Mongo, which kind of use something more like JSON as their storage format and deal with somewhat more loosely structured data. And then, of course, there's all the proprietary stuff, which can be anything at all. So there's binary files, image files, video files, audio files, and just dumps of arrays, pixel arrays, whatever. And I guess you face all of those depending on what you're doing.
Yeah, CSV file has been with us for quite some time as the comma-separated or character-separated values.
Yes.
So where does it actually come from? I encountered it first back in my spotty use when I dealt with Excel.
I don't know who first used it or where it first came from, but it's kind of a very, very natural way for anyone to write data to disk or through a pipe. So the advantage of it is that pretty much anything can read it. And these days, even if that's Unicode data, maybe in UTF-8 encoding or something, that's still easy. The disadvantages are, of course, that it's very ambiguous and it doesn't carry any metadata. By default, doesn't carry any metadata with it. And so, there's the question of how are the row headers? What are valid row headers? How do you know the types? What happens when the apparent type changes halfway down the files? It's kind of the format that everyone can use, but everyone hates because so many problems come from data being read incorrectly from CSV files.
But JSON should make it a little bit easier these days, shouldn't it? Because I think it's more structured, and I think you can encode things like the type a little bit more clearly than you do with CSV.
So JSON has a couple of advantages. So I think some people would say it's the best thing that came out of JavaScript, actually. But it has a few simple types. It only has one kind of number, so it doesn't distinguish between floating point values and integers. But because it's text-based, you can put the decimal point in or not, and that gives a strong indication. It understands Booleans, true and false. It understands strings. And it understands lists and dictionaries, as long as the dictionaries, that is a mapping from, in the case of JSON, it has to be a string, a quoted string, to some other value, which can then be any other type, one of its basic types, or another dictionary, or a list. It's pretty flexible, and it has very unforgiving parsers. So if there's anything wrong in a JSON file, almost all JSON parsers will refuse it, which in my view is a very good thing. It's the opposite of HTML. The fact that it's unforgiving, as in if there's anything wrong with it at all, a missing quote, a missing comma, an extra comma, whatever, it will refuse it. And so that makes it slightly more difficult to write by hand, but it means that there is almost no bad JSON in the world. The format specified is UTF-8 as well, so it's very good from that point of view. One of its limitations are it doesn't have any kind of understanding of dates or times or date stamps. So typically they have to be encoded as text, and then you have to have some way of deciding when you're going to interpret a field. The other thing that's very interesting about JSON is it allows hierarchy, and therefore it's good for not so much unstructured data as more variable data, tree type data and things like that. The other downside of it, which is a fairly small downside, is that I suppose there are two. First of all, by default, it's quite verbose, because if you have each data item has a label in a dictionary, typically then the labels can be repeated very many times. That's not a very big problem because you can just compress them, but it does mean that a raw JSON dump will typically be very large compared with a CSV file. The other thing that can be slightly challenging about JSON is that typically if you have a large number of records in a JSON file, you have an opening separator at the start, either the start of a list or a start of a dictionary or something, and a close at the end, which makes it just a bit more difficult to process bit by bit. A way people sometimes work around that is to use what's sometimes called JSON-L format, where each line is a JSON dictionary, often with common keys, but there doesn't have to be an opening for the whole collection at the start and a closing delimiter at the end. But other than that, it's a useful format.
It's interesting you haven't mentioned YAML, because YAML is used in computing as well. But is it actually used in angst when it comes to data processing and for machine learning and AI?
Yes, YAML. I suppose it's not a coincidence that I haven't mentioned YAML. I hate YAML. It is
okay.
A lot of people love it. I mean, a lot of people have a very great fondness for YAML. So YAML has very similar capabilities to JSON, but it's easier for humans to type, and it's a very forgiving language. It's quite hard to type stuff that isn't valid YAML. And in the same way that I was saying, a good thing about JSON is that its parsers tend to be relatively unforgiving. It's not exactly that YAML is forgiving, it's that most things are valid YAML, and it will find a way to interpret it. And very small differences, like the presence of spacing or whatever, can have a very big effect on a YAML file and change its meaning very dramatically. Some people love that. If you think about the two classic things that people know that are forgiving and unforgiving, HTML has always been incredibly forgiving. You can put almost any old rubbish in an HTML file, and browsers will bend over backwards to interpret them in some useful way. And XML is totally unforgiving. Again, if there's a single stray character, it's mandated actually in XML that an XML processor will reject the data. And YAML is much more like HTML. It, in practice, is very forgiving. Easy to type, therefore, and JSON is unforgiving. There's a law actually called, I think it's Postel's law, which is that things should be forgiving in what they read and strict in what they write. And that's not a bad principle. But my view is that in the end, strict formats mean that there's less bad data around. You know when you've read something correctly, that ends up being more beneficial. There are many opinions.
I know, but I think when it comes to machine learning or AI, then cleaning up the data very often is a very laborious task. From that point of view, having a mechanism that enforces a strictness to adhering to the rules of how you write a file is probably welcome, and it makes the life of data scientists and data processors easier.
Yes. And of course, you can have, with any format, you can extend it with more metadata. So you can have a description of your CSV file saying what the separators are, what the quoting rules are, and so forth. That can make everything much more reliable. It's something I always try to do.
The next question is around Python and how Python can help digesting data and what kind of libraries are used, particularly when it comes to large data sets, because I think in AI and machine learning, you deal very often with large data sets. So what does Python bring to the table?
Python brings an enormous amount to the table, which is the reason why it's one of the two major and probably the preeminent, in fact, system in use in data science. That and R is really the other. Python is a surprising choice for data processing or data analysis at some level because it's an incredibly slow interpreted language. And if you write all of your processing code in native Python without anything to make it fast, it will be potentially hundreds or even thousands of times slower than a compiled language like Rust or C or something. But in practice, the reason it's good is that what people should do and do in almost all cases is use very highly optimized C libraries, C or Rust or whatever libraries to do the processing. So the granddaddy of those in Python is a library called NumPy from Num Focus. There is some dispute about how it should be pronounced. I think it's NumPy. Some people say NumPy or NumPy, but I think it's NumPy for numerical Python. And it has support fundamentally for arrays of data of various basic types and very fast processing operations for manipulating those arrays. And those can be one-dimensional arrays or multi-dimensional arrays. And it's a very powerful library. It's been used forever, for as long as Python's been important in data science. In fact, it was probably the thing that made Python important in data science. So that's a very good thing to use. And it's important to realize that when you're using NumPy, you only really get the benefit if you use NumPy's functions for doing things like joining two columns, adding two columns together, or summing a column or anything like that. If you iterate over the elements yourself in Python, it will be potentially slower than just using a Python list, actually. So NumPy is incredibly important. More recently, pandas has become very important.
I wanted to talk about pandas, because I think a lot of people are using that now.
Yeah, so pandas is a library I don't use and don't like, but it's very popular with data scientists because it started off being very closely linked to NumPy. It basically provided a data frame, which is, you can think of it like a database table, essentially. So a set of named columns, at least in the simple cases, a set of named columns for a number of rows and potentially for a very large number of rows, as with NumPy, and operations for processing that data frame and for displaying that data frame and so forth. That's become very important as well and is used incredibly widely in Python. And then there's a library called SciPy, or at least I call it SciPy, scientific Python. I had a colleague who preferred to call it Skippy, but
that's for another day.
SciPy provides a great number of scientific and statistical functions, and it's compatible with both pandas and particularly NumPy. So that's very useful for distributions and sampling and convolution and all sorts of stuff like that. And then there's a library called scikit-learn, which is again, incredibly widely used. And that has a lot of machine learning paradigms that are efficient and which will operate typically over NumPy columns, NumPy arrays, or pandas arrays, or pandas data frames. So those are probably the most important things historically. And all of those are written in C or some other compiled language and can be incredibly efficient, just as good, in fact, probably better than you would typically write your own. More recently, a library that's becoming very popular and has some of the same sorts of capabilities as pandas is a library called Polars.
Uh-huh.
Polars is written in Rust. It's incredibly fast, very efficient, and very safe, but it also has Python binding. So again, you can use it directly from Python.
How's
And
it spelled, Polars?
it's spelt Polars, and sometimes people put a dot before the RS. The RS comes from Rust, I
Rust.
think. And it has adopted many of the lessons from databases. It has a query optimization stage, and it also supports parallelism. And parallelism, we've talked about, what do we mean by big or large in the context of large data or big
Yeah.
data? And there are various different scales that are interesting. Obviously, Excel started with a limit of 65,000 rows and then had this important moment about 10 years ago where it expanded to cope with 1 million rows of data. But those are tiny data sets by the standards of modern data science. In terms of the sizes that we really think about, one question is will all the data fit in memory on whatever computer you're running on?
Indeed.
And really, when you say it fits in memory, it probably needs to fit in a few times in memory because you typically have multiple copies of things lying around as you process it. If it will fit in memory, then your life is relatively easy. If it won't fit in memory, then everything becomes harder. And at that point, you need either to write fancier code to bring it in pieces, or to use a database that will just do that for you. And there are some very high performance databases, and that's another way of doing all of this stuff. Or you need a library like Polars, which will kind of handle all that for you. So one dimension of the scale of data is just storing it and accessing it. The other question is how you process it. And obviously the machines that we're sitting in front of, I don't know what you're saying, I'm sitting in front of a Mac Studio that has 20 processors. Even my iPhone has about 4 processors these days. So we all have these shared memory parallel machines. And again, if you just write code in Python without taking very special care, you will only use one of those cores. What you need in order to process really large amounts of data is to use multiple processors or multiple cores or whatever, either in the sense of a machine like we all have, or a much bigger cluster somewhere where potentially the data won't even necessarily be stored in one contiguous bit of memory. It might be distributed across various machines or whatever. And of course, the other libraries that we should probably talk about there are the various neural network libraries that are important, both because neural networks are a bit specialist, but also they are key to a lot of the image processing and speech processing and video processing. And these LLMs are obviously neural networks, deep learning models, if you prefer. And again, there are a number of libraries like TensorFlow, which are parallel and are available with bindings in Python. There are quite a lot to choose from these days, actually. Those will also potentially use GPUs for compute. So the graphics processing units turn out to be pretty good very good for kinds of matrix vector multiplications that are the basis of neural networks.
Yeah, that's quite a lot, actually. Probably people won't start with all of them at the same time, but I think NumPy is probably a good place to start.
I think most people these days would start with pandas. I personally think that pandas gives you quite a lot more, though there are a number of things that I think are not fantastic about pandas. Its null handling has always been very strange, and it has a very complicated indexing scheme that can mess with it. But nevertheless, either pandas or NumPy are definitely the right places to start. And as I say, the key thing is to make sure that you don't just use them to store your data, but you use their functions and methods to process the data, because that's where you get the performance from.
Thank you very much for your time today, Nick. That was very insightful, and wish you all the best for the future.
Okay, nice talking to you again, Peter.
So people, you heard it from Nick. If you use libraries such as NumPy and Pandas, then make sure you use these libraries for the data processing part and not just for reading in and storing data. These libraries have a highly optimized code written in C or other languages like Rust, as in Polars, that sit beneath the veneer of Python you, the end user, will be dealing with. You will find the material for this course on the Moodle platform at UCL. This podcast is produced by Peter Schmidt. The music comes from Daniel Lindenblatt in Berlin, Germany. And finally, thank you for listening, and I hope you enjoy the course. And with that, goodbye.